So good morning. I think it's still morning. Yeah, good morning. My name is Robbie Cowart. I am from Gulfstream Aerospace, and I'm the director of Supersonic Technology there.
Good morning. My name is Peter Iosifidis. I am the program manager for the X-59 Supersonic demonstrator that we're building for NASA.
I'm Laura Smith Velasquez. I am the principal investigator for the Sonic Boom Display, and I work for Collins Aerospace in the Avionics and Advanced Flight Deck group.
And so there was we had the pleasure of having Mark Kohler of Gulfstream providing a keynote just a couple of days ago, and people tried to pin them down about, are you looking at urban air mobility, are you looking at supersonic technology, and he was able to dodge the questions pretty well. And then here we have Gulfstream doing research into supersonic. So we're all interested to hear, what you're up to.
Okay. So would you like to talk first, or you want to do the presentation?
No, we'll do the presentation.
Do the presentation. Okay. Can you guys key up mine? And I think the clicker is actually up here.
Oh, sorry.
That's okay. Give that a second to load. How many of you, while it's loading, how many of you in here know about Gulfstream? These three can't answer. Okay, so Gulfstream. We are a business aviation company. We build business aircraft right over in the sister city to Charleston, Savannah, Georgia, just two hours away from us here. And on the screen, you see the tails of our current product line, which includes the G280, which is our small, mid-size aircraft, all the way up to the G650 and G650ER, which are our ultra-long-range aircraft. And I'll talk a bit more about those aircraft in a minute, but first I want to brag a moment. There are two other aircraft in here, the G500 and G600, which are literally right on the verge of going into service. The G500 was just certified late last year, and a handful of those aircraft were put into service last year. The G600 is going through certification flight testing at present, and we expect that aircraft to enter service this year. The beauty of those aircraft, you've already heard Mark Kohler talk about that this week, and the insertion of technology into those aircraft with the active side stick, the digital control network, and also the touchscreen displays. And unfortunately, I wasn't able to be here for Mark's keynote, and I was really hoping to have had that privilege. But the 500 and 600 also built off of the G650. I'll ask you around the room, what do you think is your most valuable asset? Time. That's exactly right. And people, no question, no question. But each of us individually, our most important asset is our time. What do we do with our time, right? And so, as Courtney talked about earlier, what's old is new. This is about how do we bring increased speed into the marketplace. The G650 is a testament to that. That aircraft entered service in 2012. It is now 2019, if my count is right. In 7 years. Those aircraft have been out there now for 7 years. We've got several hundred of them in service. And the unique thing about the G650 from the 550, which was its predecessor, among other things related to the aircraft and shape of the aircraft and so forth, we took the cruise speed for the aircraft. The G550, its long-range cruise is at Mach 0.8, so 0.8 the speed of sound. That's long-range cruise. And high-speed cruise was at 0.85, 85% of the speed of sound. The G650, we dialed that up just a little bit. We went from 8.0 to 8.5 for long-range cruise, and we went from 8.5 to 9.0 for high-speed cruise. We did that with increased range, increased speed, and better fuel efficiency. And so it was a game changer in the industry. And we now have several hundred aircraft out in the fleet as a testament to that. And so, you know, the key message here is performance results in time savings. And so, you know, I've been in my role now for a number of years, and we've got quite a bit of technology research that we've done both internally, we've done collaboratively with NASA, and really leading up to what Peter's going to talk about here in a few minutes, which is the X-59. But the thing I want you to walk away from is time is your most valuable asset, and we're seeking to provide an opportunity somewhere in the future to bring supersonic travel back into operation. When? Courtney asked earlier, am I going to speculate on that? Of course I can't. You know, as my boss and my former boss and my current boss have all said, you know, we've always been within about a 10-year window. Probably still within about that 10-year window. It's kind of a moving timeline. But, you know, I think we're closer than ever with NASA's program working with Lockheed and with the regulatory work that's going on internationally. You know, I continue to remain encouraged that there's coming a place when this is going to happen. So with that, how many of you in here have actually heard a real sonic boom? Okay, a fair number. Okay, so you know what an N wave sounds like. You know what the startle that can occur from an N wave. You know, if you know it's coming, it's one thing. When I was out at NASA Armstrong for a meeting one day, we were walking from one building to the next, and we happened to walk through the doors. The door clanged behind us, and as soon as it did, pow-pow, pow-pow. 2 aircraft, a test aircraft and a chase aircraft right overhead, and it made me jump, right? And I had been doing this for a number of years. It made me jump. That's what we're trying to solve. We're trying to work to the point where you can take that startle, you can take the crack out of the boom. If you look at the F-18, Ed Herring actually sent me the picture a number of years ago. You'll see the shock waves coming up over the canopy. There's nearly a normal shock over the canopy. There's some shocks around the inlet, or at least some distortions around the inlet. There is a shock there. And then shocks off the back end. All of those actually combine as you propagate those waves out from the aircraft. They combine into what's called an N wave. Now, for anybody who is interested, there is a book, the 6 Decades book. Dom calls it, you know, the Holy Book of Sonic Boom, that was released in 2014. The reference is there on the screen. It's probably about this thick, and it's all of the sonic boom research that Dominic Magliari and Ken Plotkin and Ed Herring and Peter Cohen and all of these guys have been able to compile into a single resource, into a single reference. And it's a phenomenal book. There's a lot of information in there. There's a lot of bibliographies in there that you can go back and look into older research. But the image you see on the screen is actually one that has, I guess it was maybe originally sketched by Dom and was digitized and put into the book. And what you'll see in the center of the image there is what's called the primary carpet, right? So when an aircraft is flying supersonically, it's generating shock waves around the aircraft. And as those shock waves begin to propagate away from the aircraft, they coalesce into what we refer to as a sonic boom. And where that sonic boom impinges on the ground is called the primary carpet. We were actually having a conversation earlier about over-the-top booms and secondary booms. The waves that propagate away from the aircraft laterally or above the aircraft actually have really complex ray paths through the atmosphere, depending upon what the atmosphere is doing. And if and when any of those rays reach the ground, sometimes they do, sometimes they don't, that's what is called the secondary boom carpet. And some of those rays are actually from primary rays that reach the ground, and bounce back up and go out. I'm reminded of a story that I told a propagation guy, and he laughed at me. I told him I was in my neighborhood pool one day, and I just happened to be in a very shallow area, and I moved my hand through the water, and I watched the shadow pattern on the bottom of the pool. I don't know, it's maybe a foot deep. And it was like, wow, that's intriguing. So I did it again, and so as the engineer in all of us, right, then okay, so we're gonna do it here, now we're gonna do it against the wall, and I turned it into my own little experiment, but I was really fascinated when I would move my hand through the water and I'd watch the wake through the surface and the shadow on the ground, and then I'd watch this thing way over here just pop up, and it's like, okay, where did that come from? That's what that secondary ray path is. And so, there's a really complex set of mathematics that go with this. And the guy that I was talking to actually has a water tank that he does similar experiments with. And I guess I would just say that this is a really hard problem. And anybody that is working it or has worked it knows that. If you haven't worked it, just take my word for it. It's a really hard problem. But that said, we've made progress. I'm going to let Peter talk the technical details. What I wanted to bring to the table today is, well, why haven't we already done this? In the early 70s, the FAA put in place Part 91, 817, which is the rule on sonic boom. And it basically says that no civil aircraft is allowed to operate at a true airspeed of Mach 1 or greater over the continental United States, over U.S. soil. So no aircraft can operate, no pilot can operate an aircraft, and so it basically put a speed limit in the sky that says you're not allowed to generate a sonic boom that reaches the landmass. In fact, there's actually a paragraph or a subparagraph that says you cannot operate an aircraft such that a sonic boom reaches the soil. So you can't go off the coast just far enough to go supersonic, but put a boom on the ground on the landmass. That's still illegal. You can go out further, but you can't do it where it reaches the landmass. And so for a number of years now, we've been working with the organization that's listed here. It's called ICAO, the International Civil Aviation Organization, and their Committee on Aviation Environmental Protection. It's CAPE. Sometimes you may hear it talked about as ICAO, sometimes you may hear it talked about as CAPE, but they have a specific working group, Working Group 1, that is charged with aviation noise. And Working Group 1 meets 2 to 3 times a year, and we come together and we talk about what's going on within the area of sonic boom, what's going on within it, and how regulations might need to adapt to accommodate those. So we've been working with this group, which includes the FAA and many regulatory authorities around the world now for, unfortunately, quite a number of years, but that's what it takes to get international regulation. And one of the topics, and actually we'll be in a meeting next week, one of the topics, we'll spend about a day to a day and a half on sonic boom, and we're referring to it as en route noise. Because, as soon as you use the term sonic boom, there's a negative connotation associated with it. It's a boom, it's a loud noise, it's a startling noise. And so there's been work, talking about, what words to use. Laura mentioned earlier a puff, a thump. In fact, I think we've even got a trade name called Whisper, that we put out there a number of years ago. Who knows where it's going to land, but clearly it's associated with en route noise. It's noise generated from the aircraft when it's en route. And so routinely we talk about the state of knowledge for sonic boom, and we also talk about industry and what's going on in industry, what research is happening, where industry is working with NASA or other research agencies. We have European involvement in this, we have Asian involvement in this. And so it's quite intriguing to participate in this. So I think I've got 2 more slides here. So this is just a snapshot. It's a commercial. So there was a test done just this past November down in Galveston, Texas, and you may have heard about it. It's referred to as QSF-18, Quiet Supersonic Flights 2018. It was funded and orchestrated by NASA. And there's actually a website there, nasa.gov, QSF-18. There's a whole bunch of stuff you can read about it. And just as a commercial, there'll be more information at the AIAA Aviation Conference coming up this summer. The Acoustical Society is probably going to have some papers in it. And so, I'd encourage you, if you're interested, to, go look at those publications. But what this was, really was kind of a risk mitigation exercise. It was a precursor to what's coming with the low boom demonstrator, where NASA took their F-18 research aircraft and they performed this unique maneuver where they put the aircraft into a dive, accelerate supersonically, and they create a series of waves that, as they build up, they impinge upon the ground and they create the noise, which is kind of akin to what is being anticipated with the X-59 aircraft. And so it was really aimed to look at, how to collect information. How do you record the booms on the ground? NASA's been doing this for decades now, right? So we know how to measure sonic booms. But how do you also gather the data to assess people's reaction to those sonic booms? And so they basically, gave people a website. Here, respond. Put your when did you hear it? What did it sound like? Did it annoy you? Did it startle you? Did it interrupt what you were doing? And so all of that data was captured and is right in the middle of being processed and put into a form where it can be disseminated in a fashion where we can digest it. Because right now, when you're overwhelmed with a mountain of data, sometimes you got to take the time to figure out how to digest that information. But one of the key things here is this was the first sonic boom test over a civil community off-range, off of Edwards Air Force Base in probably 60 years. And NASA didn't get thrown out of town, so that's a good thing. And it's really encouraging to see, and for those of us who were down there and got to participate, just how noisy our environment is around us and how this sound that we're anticipating that we'll be able to produce in the future would play into that ambient environment. And I guess the last thing here is I had to show our quiet spike. This was a test program that we did probably, I think we finished up flying in 2007 out at NASA Armstrong. And, we're still working this. We're still leaning on this, both on the technical front, on the regulatory front, and even on other fronts. And I'll just tell you that, hopefully, in the not too distant future, maybe within 10 years or so, maybe we'll be able to do this. It's really hinging on the regulatory front, quite honestly. That 91.817 is just one piece of the equation. It's like people ask me, well, when are you going to put a quiet spike on the front of a G650? It's like, well, great, we can do that, but that doesn't solve sonic boom, right? You have to generate the whole aircraft with sonic boom in mind. The regulatory timeline is clearly pacing technology, and until the regulations are in a place where it's favorable, you're not going to see Gulfstream move on it. You're not going to see really anybody move on it. But as I said, 91.817 is one part of the problem. There's Canada, there's Europe, there's Asia, there's Africa, there's South America, and this truly has to be a harmonized effort across the globe, and that's really where our focus is.
Wow.
So with that, I'll hand it over.
That's great. I appreciate that. So there will be a Q&A session after, so if you don't mind formulating your questions and holding off, this will be an interactive panel, so feel free to craft some questions and we'll address them. So Peter, if you don't mind talking about what you're working on.
Okay, thank you. I think somebody's going to be loading the next presentation here. So while we're waiting for that, I think given the, like what Robbie said, given the environment that we're in here today, it's very unlikely you would hear an airplane flying over that's generating a low sonic boom that you would even notice it, given the, the conversations that are going on around the room. But okay, so here we are, 75 years at the Skunk Works. We've been doing this for a very long time, so this actually, the anniversary was last year. So I'd be amiss if I didn't at least talk a little bit about some of our history before I get into the X-59. We started out in 1943. Here's Kelly Johnson, which is really the person that started the Skunk Works and espoused the innovation and small empowered teams that can do great things for urgent national needs. I mean, that's really how we got started. And yeah, you can see near the top there the X-59, or low boom flight demonstrator in 2021, but what you see below that is a lot of the other aircraft and some very iconic aircraft that have been developed over the years at the Skunk Works. Certainly some of the ones that are very famous to most people and a special place in my heart, SR-71, F-117, U-2, those are just tremendous aircraft that provided a lot of benefit to our nation. So going into low boom, in the history and in the future, as Robbie was saying, there's been a lot of research done regarding sonic boom and how do we make the noise acceptable to at a level that will be embraced by the community, because if it's not, it's never going to happen. It's really about convincing the population that this is not something that's going to be disruptive and will be acceptable when it comes about. And as Robbie mentioned, right now, we can't fly an airplane at supersonic speeds. It's against the regulations that are out there, except for very unique cases of supersonic corridors for the military. So who's doing this? Who's actually taking the lead on this? And this is really a NASA effort, and I have to really give credit to NASA to take this this step and this endeavor, because the reality is the government put the supersonic overland regulation in place that doesn't allow anyone to fly supersonically, and until the government takes a lead in removing that prohibition, aircraft manufacturers are not going to go out there and build supersonic airplanes that they can't fly. That is a tremendous investment, and if NASA wasn't taking the lead on this, we would be stuck at subsonic speeds maybe forever. So this is one of the strategic thrusts that they have, which follows their 3 mega drivers as far as achieving a low boom standard, and that's what this project is about. This airplane that we're building is basically a noise generator to achieve a low boom standard, and repealing that supersonic flight rule that's there today, replacing it with that commercial standard, and then allowing aircraft manufacturers to go out there and build products, whether those products happen to be business jets, which is very likely to be the early adopters of this technology, or commercial airliners. So the question posed earlier is, well, okay, well, why didn't you do this 20 years ago? Why are you waiting now to do it? I mean, going faster, it's something that we've all wanted. Unfortunately, we were never, until recently, in a position to say that we could actually do this. And this was a test. What you see here is that a test that we did back in 2011, which was really the aha moment for us to say that we're ready. The tools have matured to the point where we can do this. And what this test did is we developed a design at Lockheed Martin and felt that, okay, this is the design that's going to achieve a certain sonic boom level. So we took that design, we built a model based on that design, and then we took it to the wind tunnel. And what was demonstrated from that tunnel was that the prediction noise that we had anticipated was in lockstep with the results that we saw during that wind tunnel test. And essentially that was the aha moment that said, okay, now we can take this and bring it up into a full-scale airplane and achieve the desired result of the sonic boom that we think is going to be acceptable to the general public. And NASA has established that level to be at 75 PLDB. That appears to be the level, arguably 1 or 2 below that, depending on who you talk to, but it's around that number. And very similarly, what we experienced in Galveston during that time and all those tests that were generating a sonic boom level really between 70 and 80 PLDB, depending on the conditions and where you were at, as measured by the microphones on the ground. And it was very encouraging to hear from the general public that, hey, what did you think about that? Think about what is what I heard when I was talking to some of the people. So it was generating a sonic boom level through that demonstration that was at the same level of what this airplane is going to generate, and some people didn't even hear it. That's very encouraging. So when NASA does the full-scale community response data collection with this airplane after it's delivered to them, it's very likely we're going to be seeing the same type of results. There will be an acceptability of this new noise level, and ultimately a rule change will be forthcoming from that. Talk about a little bit about the airplane itself and some of the features that we're using. One of the guiding principles that we had provided to our designers was to essentially build the smallest airplane, the lightest airplane that would achieve NASA's requirements. The key requirement in this is really the 75 PLDB level. That's 75 or less. And it's not an easy task, I will tell you. 10 years ago, 15 years ago, we were thinking that 85 PLDB was the best we could do. However, due to technology advancements, we find that 75 is really the new standard today, and probably the standard that will ultimately be acceptable to the general public. But walking around the airplane, some of the unique things that you will see is there is no natural vision out of the front of that airplane. So the pilot is flying on basically a TV screen, if you will, and hand vision system. That XVS system is being built by NASA and provided as a subsystem to us for the airplane. It's a very long, pointy airplane, which will likely be the case in all supersonic aircraft that are going to be low boom. Fixed canards to provide that necessary nose-up trim. Another guiding thing that we provide to our designers is we want to reuse as much of what already exists versus designing new. Basically, the only thing new about this airplane is the shape. Almost all the subsystems inside the airplane are either reused, repurposed, or commercially off the shelf from other aircraft. That canopy is from a back seat of a T-38, landing gears from an F-16. The engine is from the family 414 General Electric engine. Conventional T-tail, so that's well understood for stability and control purposes. And also centerlining the engine gives us some additional shielding for the sonic boom signature. This airplane essentially is developed to meet those requirements. It's not taking into consideration other things that are different challenges that will have to be addressed by aircraft manufacturers ultimately, such as what is the L over D, what is the fuel consumption, what are the environmental concerns, what are the en-route noise concerns, what are all those things, aircraft noise around airports. Those are all challenges that will be solved, but the only problem we're trying to solve is that 75 PLDB here. So we try to do it in a manner that was most affordable to NASA. This is a little bit of our schedule and what we have in front of us. We were awarded the contract last year, almost a year ago now in April. And we're having a CDR later this year in September, and first flight is in 2021. So pretty rapidly moving timeline here. A lot of concurrent engineering going on. We don't build airplanes in the traditional fashion of waiting to get to CDR and then start building. If you did that, you would add another 2 years to this schedule, and that's not the way to do things affordably. You have to condense the schedule as much as possible to accomplish that. So regarding some of the design maturation that's going on, we're like I said, we're marching towards CDR for this summer. We've essentially integrated all these subsystems into the airplane. We've got a simulator at our facility in Palmdale where we've developed our control laws, have our test pilots from Lockheed and from NASA flying the simulator, giving us feedback as to how the airplane reacts. We've built models of the airplane and taken it to the high-speed wind tunnel test at NASA Glenn. Also built low-speed model that we've taken to Langley to look at how the airplane behaves in all those environments. And so far what we've seen is our design is sound and that the airplane behaves in the manner that we have expected it to. Here's some more pictures of those tests. The upper right-hand corner there is the low-speed wind tunnel. The one you saw previously was the high-speed at Glenn. We also did an inlet test down in Fort Worth to see how the airflow reacts with the inlet. And on the left lower-hand corner there, what you see is there the surface flow in the low-speed wind tunnel. So the one thing that that's different between this airplane and a lot of other projects that you may have seen is, you know, there's a level of realism that comes along with a project when you start cutting metal, and you've left the PowerPoint charts, and that's what happened last year. This was our first chip ceremony back in November of last year, where we started machining our first part. That was a few months ago, and we're well underway to building a lot of those parts, and we will be loading our first part into our jig at our manufacturing floor in May of this year. And this is our production facility right now, and as I look at this picture was taken 3-4 weeks ago, and I can tell you right now it's a lot more congested than what you see here. It's just amazing how fast things are coming together. So this is our production facility. We got our two fabrications almost done now. We're really ramping up our engineering drawing release. Our entire team is fully staffed now. We've got a lot of suppliers on contract. Most of the suppliers are on contract now for all the subsystems. We also have suppliers building sub-assemblies for the airplane. We're not building everything ourselves. Most of the work that we're doing is the design, and we're integrating the aircraft at our Palmdale facility, but we have a lot of small businesses and others, large businesses as well, participating in the fabrication and the design of this airplane. So like I said, the first jig load is in May of next year. You will probably start seeing a lot more information about this airplane. We plan to have time-lapse photography on our production floor, which is very unusual for our Skunk Works operation. Most of the work that we do, we can't tell you about. So this is actually really an honor for me to be able to talk to you about what we're doing. It's just something that we don't typically do. You'll hear about what we're doing behind that wall right there and others 20 years from now. That's about how long it takes for something to become public. But we're very encouraged and really proud to be a part of this with NASA and being able to ultimately bring faster travel to the general public. I know for all of us, or a good portion of us that flew here today, how great it would have been if we could have got here in twice as fast as you did. And then when you really extrapolate that to going to some of those really far places, like for me, I live in California, going to Asia, to Narita, Tokyo, in half the time, in 6 hours versus 12 hours, what a great benefit that would be. As Robbie said, that time is one of the things that we actually have some control over, and what if we can get some of that back through travel. So with that, I think I'll wait for questions to the end. I will go ahead and turn it over to Laura. Thank you very much.
Great. So now we kind of talked about airframe. We talked about some of the NASA stuff that we're actually implementing to do all the test research. So the work that I've been doing with NASA is more like, okay, so now that you've got a low boom signature, how can you manage that boom? How do you integrate it into the flight deck? And how do you get the data you need into the flight deck in order to integrate it? And then understand how those rays propagate through the atmosphere, so you can understand how to manage your flight plan in order to place it in a specific area or to make it so the boom doesn't reach the ground at the same time. And how do you do this in real time so that you can actually coordinate with air traffic control, and then also not require the pilot to be a physicist in order to manage their sonic boom, because it is very complicated and there are many, many degrees of freedom. So I'm the principal investigator for the sonic boom display project. And the background is NASA has been developing this algorithm for years. It predicts the magnitude of the sonic boom and how it generates at a particular velocity. Their original algorithm just used weather balloon data, and then it was also hard-coded to Edwards. So one of the things that we were wanting to do is take it and integrate it with a terrain database, integrate it with a weather data service, and then also take that so that you could implement it and integrate it into a flight deck. So we had a 2-year NASA contract to the conceptual display prototype. It's actually in software on a tablet, and we integrated into the Quest simulator at NASA using the low boom flight demonstrators data and performance data to test it and see how it reacted and how well the algorithm performed. So we actually had the weather data analysis and then also a notional architecture and how to implement that. Then the 3rd year follow-on we just finished up was foundational capabilities for all that weather data integration, and then creating a pilot decision space as well as doing a weather sensitivity analysis. One of the interesting things is trying to characterize the atmosphere, right? Because we don't have bloom data, so we need a global forecast system. We need to look at the local data system. And just what's the resolution of that data do we actually need for the algorithm, for that wave propagation? But it's not only the data from the aircraft to the ground, because as we mentioned, we have over-the-top booms. So if we can understand how those rays go through the atmosphere, we understand just how much of the atmosphere we have to characterize and how that's going to affect the pressure level on the ground. So it's a lot of the information. So it's kind of a 3-part. So you have the notional architecture, you have the human factors, you have the avionics integration and the data, and then you also have all the weather sensitivity and the weather data analysis. So we completed a concept of operations and conducted pilot working groups. So we're now Collins Aerospace. So I left the Rockwell Collins on there. But we have flight operations, and I also used Concorde pilots and NASA Armstrong pilots, because one of the biggest issues right now is we have supersonic pilots and we have commercial pilots, but we don't really have supersonic commercial pilots. And what is the task going to be? Well, how is the flight deck management going to change? How is the coordination going to change? So really understanding that was really key to how you're going to integrate and design the system for pilots to be able to easy to use. One of the big aspects was also how to create a pilot decision space so pilots can understand really quickly how to manage their boom. So we automated a lot with automated route assessment, but then also mock altitude combinations, showing them where their lateral combinations are, and then also a threat detection, right? Because if you're going to bust your noise abatement level, you need to know when you're going to bust it and when you're not going to bust it, and then being able to show them that, but then also be able to show them a real-time prediction. And this is key. Today, we finally have the processing capability to do all this. So what people don't realize is every few seconds, you're calculating one ray trace, just one, all the way down to the ground. That's a lot of processing. And we have the capability and improve the algorithm so much that we're able to do this real time. So a little bit, we have the real-time display. This is very technical, so I'm just going to show you a few pictures. But you have the real-time display on the top, and then you have the pre-computed footprint. And being able to update your flight plan real-time in flight and do all this trajectory planning, but not only that, have the system do it for you. So there's actually quite a bit of work that we've done ourselves to automate this whole capability in the system. Go past all the data. My engineering disclaimer. I'll get to the final slide, you guys. There you go. So this helps a little bit creating a pilot decision space. So we actually go through and do similar to trajectory planning, to where you're actually figuring out what is the least amount of change in your flight plan that allows you not to pass that threshold for your boom threshold on the ground. And then we map that out to the pilots. Now, if you're not a pilot, this might be a little bit difficult to look at, but we actually use the vertical plan display, and you have a Mach line there, and then a line that shows you, okay, if you can change it by going altitude, then you have the green and you raise your altitude. If you can't, then you actually must need to do a lateral move, or you have to change Mach as well as altitude. So it's a lot to go into, and I won't go into all of it here. Some of you went to my presentation, but feel free to ask questions later. And then I'll kind of sum up, you guys. Oh, wait, back. But anyway, to sum it up, with the sonic boom display technology, we're on our way to breaking that noise barrier. So we finally got the noise low enough, but we also don't want to place focus booms. We also want to have this ability to fly Mach cutoff, which is where if you're high enough based on your airspeed and your altitude and the characterization of the weather, you can actually make it so that your sonic boom goes down and then refracts upwards before it even hits the ground. So you're not even hitting the ground. And providing the pilots the knowledge and the capability to manage their flight plans so that they do those enables supersonic overland flight. So, okay.
Fantastic, thank you.
All right.
So we'll back up a little bit. 5 years ago, I had the privilege to moderate a panel at AeroTech, and the folks sitting on the panel, we were asking them about, where their focus lies for R&D. What's the next best thing? What's the next disruptive technology? And certainly the audience asked about supersonic, hypersonic, and so they wanted to know what everybody was up to. And the panelists all just looked at each other and looked down. And then Boeing, a gentleman from Boeing, finally said, "Listen, if there's a market, if people are willing to pay for it, we'll deliver it." So what is driving the market?
Good answer. It's an interesting question because, we see innovation all the way through the aircraft. And it's not just in the aircraft itself, it's in how you use the aircraft. I talked about time earlier. The cruise segment of a flight is only a portion of that flight. There's the get up there and the get down from there, and there's the get on the airplane and get off the airplane. I mean, there's so many things that are associated with, managing time. And it even goes into, what does it take to get the airplane started up and prepped and ready to go? So, for us, there's no one single answer for it. We're constantly looking at improvements in the cabin, improvements in the flight deck, improvements in the airframe, improvements in the systems and propulsion integration into the aircraft. So it's everything. And anybody out here who is works for an airplane company, they know that, right? That said, what are we not thinking about might be another question for another panel.
So what I get asked a lot is, what are the technical challenges regarding X-59? And I will say that really the technical challenge for the most part has been solved, where we believe we have the design methods now to develop a shape that's going to create this low sonic boom noise. And that was really accomplished back at the preliminary design level before we moved on to what we are now into now, which is the detailed design of the airplane. Right now, there's a lot of hard work that still needs to be done as far as integrating all the subsystems and make sure they all talk correctly to each other. But now it's just building the airplane. The technical challenges have really been solved. And very much in tradition with Lockheed or the Skunk Works, we try to solve one miracle at a time. We don't want to put so many things into one project where if one doesn't work, the other 5 great things you did really don't matter. So in this case, we're really using the design methods to create that low sonic boom level, and we believe we're already there, and that's based on really on our ability to deliver that design solution using NASA tools and having NASA say yes, that solution will actually achieve the desired result that we're looking for.
Right. So let's get into the nitty gritty. If we look back at our history, certainly we look at the Concorde, and it was kind of luxury and the more affluent folks that were taking advantage of it and driving the market. But the criticisms of it and part of the reasons it was the program was retired in 2003. Noise, fuel, more than half of its weight, fuel consumption, and then just safety concerns. There was one event with 113 fatalities, which didn't help, and it certainly wasn't. They found that it wasn't the fault. Nobody was held responsible associated with the aircraft design. But so what's different now? What's the enabling technologies that are behind fixing those kind of issues?
Everything. Everything.
Yeah. Well, you had mentioned it's a whole aircraft design, every part of it.
Well, I think Laura mentioned it a few moments ago, and you might want to build on this. I mean, the computational capability that we have now, and Peter, I think you even said it, when you got into the wind tunnel, right? The things that we can do now, today, we couldn't do 5 years ago, 10 years ago, 20 years ago. We had to do them in different ways. Let me say it that way. We had to do it experimentally. We could not do some of the computational stuff that we can do now. The tools have come along. Both the software tools and the hardware tools have come along. As Laura said, when you start taking a single ray and you propagate it for a certain step size with a certain resolution all the way to the ground with a certain resolution of the atmosphere, with a very specific frequency content, and then you do that all the way to the ground at every one of those ray angles, and even the ones that go over the top, it's quite impressive, actually, when you think about it. I mean, I can tell you, what used to take us a month of computational time, there was a place in time that it only took us a week. Went from a month to a week, and then we went from a week to a day, and then we went from a day to maybe hours. And that scale just keeps going.
And my prototype does an entire flight for Texas to California in a matter of seconds.
There you go.
For the entire flight, as well as the threshold calculation, comparison, and impact assessment.
I'll add on to that as well, because the design that we've developed for the aircraft, as Robbie mentioned, 5, 10, 15 years ago, it would have been an entire effort to go recalculate something that changed on the airplane. And as you do trade studies, even from preliminary design to detailed design, you will find things that change. That's just the configuration does. And you have to be able to account for all those changes, and you have to be able to account for them quickly so that you don't have a schedule problem or a cost problem, because you can essentially learn what the answer is very quickly. 10 years ago, maybe it would have taken a week or a month to identify that new solution to that problem that you identified, because the actuator that you had selected is not available, and you had to go to a new actuator that created a different blister on the airplane that will now cause a different shock that you have to account for in your entire solution. Now you enter that into the new supercomputer, and within hours you already know what the impact of that new blister is. So having that ability of those tools and the computer speed that we have today just allows us to really quickly go through the design solutions and know the answer so fast that the impact is minimal, allowing us to keep marching forward at an ever so quicker pace than we were ever able to do in the past. And that is an incredible advantage And it's not only on computers regarding design analysis, but even manufacturing. And every time something changes, we are literally looking at that analysis to see how the noise level has changed. And I will tell you, it literally gravitates, you know, I won't say daily, but every week we have something that we have inputted into the solution that we can change. And even the way we fly the airplane and you know, where the flight controls are set, there's different levers that we use to be able to achieve the desired sonic boom level that we're looking for. One thing I didn't mention during my presentation was the T-tail in the back. I don't know if many of you noticed that, but that is not a control effector for the actual aircraft. It actually is the control effector for the plume and the sonic boom level. So we're able to actually trim that and affect the sonic boom level as well. So having those capabilities regarding computing power and software power is just incredible compared to where we were 20 years ago. I mean, how many people here in this audience don't have a smartphone, right? Everybody has one. How many people here had a smartphone 15 years ago, right? Same answer. So things change, but what really has changed is 15 years ago, many of you could have had one had you had a lot of money, right? Mm-hmm. But now you can have one and you don't have to have a lot of money. So Supersonics could be viewed in the same way. Those early adopters are likely to be those very affluent people who have the ability to pay for that business jet, if you will. But somewhere down the road, as technology continues to evolve, every one of us will be able to afford to fly faster, just like those affluent early adopters will.
And I also would like to add that we've made leaps and bounds when it comes to enhanced and combined vision systems. So enabling, you know, us to fly at those shallow approaches to where you can't necessarily physically see in front of you. You know, it's like, I like to say it like Star Trek, put it on screen. It's amazing, we're there. And now that's one of those enabling technologies. So not only the processing speed in the avionics, but all these other technologies that just enable us to actually be able to use the design of the aircraft and the low boom. It's pretty incredible, actually. Weather data, another big advancement. Just the amount of weather data we can get in the connected aircraft. It takes a lot of data to process this information and characterize the atmosphere. It's there. It wasn't there before.
And that was an aggressive timeline for NASA, you know, to have first flight in just 2 years. So it's nice that you're taking advantage of you know, digitalization and modern technologies and mining data to improve designs. Let's talk a little bit about the pilots. You know, what it's going to require. It shows my age, but it freaks me out a little bit that there's no heads up. You know, you're not looking out a window for situational awareness. So is it going to require unique, you know, training and education, and is there going to be a finite pool of pilots? What do you envision? And fatigue. You know, is there going to be a lot going on, a lot to monitor, or are we going to rely on automation? What does that look like?
Human factors want to take it.
So even as I'm a pilot as well, so it was one of the big questions that I asked, and I went through and I did a gap analysis for traditional operations of what we do today, and actually the operations do not change very much. What changes the most is being able to do that assessment in flight and automate them. Everything else, for the most part, goes right in line with your normal flight operations. But the mental change of how you think does a little bit. A lot of us pilots, we tend to fly with distance and range. A supersonic pilot thinks in terms of time. You're going so fast, distance just blows by. So when a supersonic pilot is trying to manage, they're looking at, oh, okay, how much farther ahead? When do I get there? When do I have to turn? When do I have to do all this stuff? And it's all done in time, not distance. You may not have noticed it, but because I didn't go into the details of the display, but instead of having range markers, we have time markers to give them that idea and that concept of how much information that they're going to fly. So there's a little bit of a mental shift when it comes to that, but most everything else we tried as much as possible just to keep it to what a pilot would standardly need. Now, when it comes to the enhanced vision system, a lot of those systems are already being integrated into the aircraft. They're used to using their heads-up display stuff, except now, you know, your heads-up display is gonna be a video screen, right? So in a way, that's kind of nice because we talk about going from heads down to heads up, but now it's all integrated and in with the synthetic vision system and technology. So in that aspect, that necessarily doesn't change either. And I don't know how many of you guys are pilots, but just how much time do you spend en route, you know, looking out in front when you're managing your flight deck? It's mostly just visual separation. You know, when you're up that high, you're not really doing that much of that anyway. So mostly takeoff and landing is when you're really starting to use all those flight displays. So.
Well, I will tell you, I am not a pilot, and however, I have flown our simulator, and I can tell you that for a non-pilot, and being able to land the airplane, which is the hardest part of flying, is really landing the airplane. The rest of it, you could, you know, teach a child to do as far as flying the airplane because it behaves very well. So, not having that experience and be able to actually accomplish that, you know, to me seems almost academic to a real pilot that has that level of experience. Now, granted, my life wasn't in jeopardy when I was landing the airplane because you are flying a simulator, so there's that mental aspect of it as well. But the feedback we have from our test pilots, both from Lockheed pilots and the NASA pilots, is this is an easy aircraft to fly. You do have peripheral vision, but they don't seem to really worry about the fact that they don't have the windscreen. I can actually tell you that there's more definition in the enhanced vision than there is through your natural vision as well.
That's a good point.
So you're actually getting better information through technology than you are through your actual eyes looking, trying to find something out there in front of you.
Along with navigation aids and so forth. I'll add to this, Courtney, because your question was about pilots, right?
Yeah.
So I'm reminded of a story. This is probably 2009. I was at a session in Europe with a European contingent doing European research on Supersonic, the HISAC project. And there was a Concorde pilot there with us.
Wow.
And it sounds like Laura has dealt with a few Concorde pilots in her project. And I asked him over lunch, I said, what should keep me up at night? He said, everything. Okay, all right, everything. Now contrast that with a conversation of literally within the last, I'd say 18 months with a pilot today who has come out of the military and is now working for Gulfstream. And we got to talking about, you know, going fast and going supersonic. And he said, no big deal. You know, you won't even know it. You won't even know it. The only way you'll know it is you'll see the Mach meter change. Wow. So technology, all of the improvements coming along, this is about education. That's what all of this is about. It's about education and bringing people into, you know, the Concorde pilot was dealing with 1960s technology, 1950s technology, even, as opposed to today, you're now into 2000s.
Yeah. We invite questions anytime. If anybody, oh, fantastic. Jim's coming with the microphone.
I'm coming.
I know, me too.
Hi, Bud Jackson from Boeing. But coupled with the avionics and the noise certification of that, a big leap of technology boost that has to go to this has to be the engine efficiency as well. From Peter and myself, I have a relationship with the SR-71. It's quite a ways from our Pratt & Whitney J58 days to the Concorde days to what we have now. That engine efficiency, and as you said, you don't have to carry around 80,000 pounds of fuel with you, bleed air, all the rest of those. That has to be just about as huge as anything else for making this viable.
So,
well, nobody had mentioned it. I was just thinking, isn't that one of the little key pieces, it seems, to make that possible?
absolutely, and I was trying to formulate the words. What many people misunderstand is when you're flying supersonically, especially the general public, when you're flying supersonically, the engine doesn't know that except for one thing, temperature, right? The air going through the engine is still subsonic air. You're slowing the air down to get into the engine so that the engine can operate. And many people don't understand that, right? Now we're not talking Mach 3 here, right? But when you start talking about efficiency, there have been many advances. I mean, phenomenal advances in engine technology. And when I read now in the media, quotes like 5 to 7 times the amount of fuel burn, it's like, no, folks, that's not right. That's not factual, right? Let's get facts out on the table of how much fuel it really takes to do this. Now, if you are in a military application where it's brute force, it's all thrust, push through, yeah, okay, maybe so. But for a commercial activity, you're not going to be talking anywhere near those levels of fuel burn or emissions. I mean, all of the engine technology has got to be brought forward. The problem is, to your point, there's not an engine, right? Nobody's got an engine out there. We saw just
GE has an engine.
December, no, it was MBAA. In MBAA last year, GE announced
Right,
the
I was gonna say
Affinity engine.
GE.
I remember fighting the battle with Gulfstream too. I was with BMW Rolls Royce at the time. It was 710, 715 on the T5.
Yep.
And push traffic for every mile trying to get range.
Every mile.
And even from that jump to now, and me going 787, it's just amazing to me.
Yeah. Yeah.
And what it takes out of the airplane that goes around it is just a massive.
Iterative process, right? More efficiency, less weight, more efficiency.
And that's probably why as Rob mentioned, there isn't a propulsion solution today, but there are existing cores that can be adapted for supersonic commercial travel. And it's also likely that that first commercial product is probably going to start off in the 1.4 to 1.6 Mach range, where you don't have to face some of the other challenges that are associated with faster travel, like the Concorde at 2+, where you have the material challenges, the thermal properties, and those other things that you have to solve for. You're going to see a supersonic travel solution that is fast enough that people will want to travel 1.4, 1.6, but still closes the business case regarding you have the right propulsion solution, you have the seat per mile, the range, the amount of time you're spending, all those other things that will make this a proposition good enough for an aircraft manufacturer to go build a product around. That doesn't mean that it stops there. It means that technology will continue to evolve. It doesn't mean that 10 or 15 or 20 years after that, you don't get to a 2+ Mach solution that also meets those business requirements, that closes that business case, and now you start seeing even faster airplanes.
So it'll be Part 91 guys.
It's a good place to start.
Probably so. And so now don't walk away with this is not more fuel. You're going to burn more fuel, right? There's no question about it. It's going to be more fuel burned than a subsonic aircraft. But we're not talking 2, 3, 4, 5x the fuel.
And that's as a result of the takeoff is different. Correct?
Takeoff is different, right?
Okay.
So I'm thinking maybe that was towards our conversation earlier, right?
Yeah,
So
yeah.
Concorde used afterburner on takeoff, and they did that for reasons of drag. I mean, they basically, with the wing shape of that aircraft, they had to go to very high angles of attack and very high speeds to get off the ground, and to do that, to push through that drag, they had to put the burners on,
Right.
which is noise.
Oh, I have a question.
Yeah, great panel, just fascinating topic. You talked about kind of 3 pillars to enable the technology, which is the engines, right? We talked about a little bit that, the regulations, the pacing item, and then the airframe and the boom. With regulations being the pacing item, if we get approval, what's the timeline before we get our first aircraft in production or in service?
Somebody had to ask the question.
Yeah. you're going to get a different answer, obviously, but I think once you start seeing NASA to test the X-59, they're going to know how the community reacts to that sound level pretty quickly. And I wouldn't be surprised if aircraft manufacturers start developing their minds that, you know, this is probably going to be acceptable at this level. And somebody may decide to start a product line, if you will, in anticipation of a rule change coming, or they may not, and they actually may wait for that rule to change. But I would suspect that given that the results that are expected to be seen from this consumer response data collection, that a manufacturer will likely want to be a first mover and capture that market initially, and will probably make a bet in that direction that this rule change is coming, and it's likely coming at this level, and let's design around that level and build a product that will satisfy that faster demand. Now, there's other problems that we talked about that have to be solved as well. Some of them not so if you're talking about business travel, and that's why I believe that first adopter will probably be a business jet versus an airliner.
So like I guess the booms and the Aerions, they're doing the only over water, right? So
That's
No.
correct. That's correct.
is that not
Well,
correct?
they're doing Mach cutoff.
Yeah, so Ariane is doing Mach cutoff. Boom is doing over water.
So
Two different types of operations.
okay, thank you, thank you. So would they have an advantage then? You would think they would if the rule changes for overland operations, or is it a totally different design problem?
Well, I think if maybe you could tell everybody what Mach cutoff speed really is versus flying supersonic at 1.4 or 1.6 might
Yeah,
be.
so mostly Mach cutoff, you're going to be close to 1.18. It's much slower, but at the same time, your boom doesn't reach the ground. But if you can fly over land, even if you're much slower, the airports that you're able to fly to are many, many more. So now Boom, when I've talked to them before, they are looking at coastal offsets and some overland flight, but it would be at a subsonic speed. So the idea of not having to slow down and then speed up again is very attractive. So, but, you know, at least they are not wanting to wait until legislation comes out, whereas the others.
So there's a couple of pieces to the legislation. What we have been talking about is sonic boom, right? So
Right.
it's supersonic flight over the land mass of the U.S. or other countries. There's also other regulation that has to come. The FAA made an interpretation of FAR Part 36, which is landing and takeoff noise, just in the last, I'd say, well, I guess it was probably last year, 2017, 2018, which said that the current U.S. regulation for Part 36, Chapter 36, does not apply to supersonic aircraft. It only applies to subsonic aircraft, and therefore, that means there's not a rule for landing and takeoff noise. And if you followed legislation, the FAA reauthorization of 2018 was put in place and has charged the FAA to now develop just that regulation.
Right.
And I think their deadline is to have an NPRM out in early 2020. And so they're working on that right now. And that piece would apply to all of those aircraft, whether the first aircraft is a supersonic over water only, or whether it's a Mach cutoff, or whether it's a supersonic over land. So that is needed. And the thing that some people don't ask about is, what about airworthiness regulation, right? Are there any changes or new additions that are required for that? And that's a question I can't answer yet. I mean, it's certainly something that we are looking into, and we're talking to our counterparts about. But that question is still yet to be answered. I hope that helps.
Yeah.
And there's a lot of work being done. I know SAE is bringing together subject matter experts like yourselves to establish standards, which will inform, regulatory bodies and that sort of thing. Feel free to.
Yeah,
We have a
over there.
question. Great.
Good morning.
Good morning.
Serge Royot, Dassault Aviation. how you deal with customer expectation with its much comfort in the cabin and the supersonic, which reduces the size of the cabin.
I didn't quite understand.
No,
all
no,
that.
I'm sorry. One more time. Or try.
So what he's saying is his business customers expect a certain size of cabin, but Supersonic reduces the size of the cabin. Can you elaborate a little on that? Or how do you deal with
The
that?
answer is yes. Yes, they do expect a certain size cabin, yes. And Supersonics is going to challenge that. And so the answer is, I don't know yet, right? But it certainly is something that is near and dear to our business model. You know, we believe a G2 size cabin is maybe the starting place. A G650 cabin would be fantastic. But it's probably somewhere in between those two, maybe. So a G2 is probably 12 packs, yeah, and 650 is 19.
So can I follow on real quick? Are you pursuing different technologies for the structures to make that work? Are you looking for additional solutions on the material side, or shaping?
That's probably a great question for the engine
Or is
company.
this all,
Because
or
it
is this
really,
all proprietary stuff? Yeah.
Well, he's talking structures. He's talking structures, airframe, right? So if your cruise point is less than 1/8, you can probably get by with conventional materials, right? If you're going to go above that, then you're going to need higher temp materials, a little more exotic. It's not that they don't exist; they exist now.
Right.
We were discussing before the panel earlier, and Peter even mentioned it's like we build aircraft today within the industry that fly supersonic every day of the week. So it's not new, but it's dependent upon the application. So Jim, it is a good question, and certainly when you get into the engine side of things, when you think of military engines. The MTBO's not a long time at really high speeds. So there's some work to do.
Well, let's talk about that a little bit more because honestly, from my perspective, we're looking at business jets, commercial jets, flying faster than the speed of sound. What are the considerations? We had talked about materials, power, noise, flight deck, and I don't want to say kludging together, but taking advantage of commercial off-the-shelf technology to bring the best solutions together in an aircraft design. Can you comment a little bit about that, about the genesis of it? Starting with an existing airframe or model or.
well, I think any solution is going to have to consider speed, range, fuel consumption. Those are probably the primary drivers of any that will all have to be considered around those three things because you want the maximum speed, you want the least fuel consumption, and you want the most range, obviously. And you have to do it in a manner where you can sell that product, whether it be the airplane or a ticket or a seat on an airplane, in a manner that people feel they're getting value from it. So all the technologies and solutions are going to have to be wrapped around those three considerations. And the propulsion system, and I keep coming back to that unfortunately, is really the piece that has not yet been defined or solved yet. Building airplanes is, again, something we do very well. And for military applications, you don't have the considerations of, to the extent of fuel consumption that you do in a commercial environment. Yes, they do consider that because at the end of the day, they still have to pay that fuel bill, but it's not as a big a consideration from a value standpoint because they have a different mission. It's a different way of using the airplane.
And something that's also interesting is some aspects of reducing your boom signature on the ground are actually opposite of the way you might want to fly. For instance, flying with a tailwind. You have a very strong tailwind, it can actually increase some of the boom, whereas then you don't get the benefits of fuel if you're flying with a headwind. So there are those type of optimizations. The neat thing is there are other technologies that are also being developed for optimizing that type of problem based on what your weather is, your reroutes, your fuel optimization, and including the boom optimization. So.
Can one of you elaborate just a little bit? How much does that change the flight envelope? That like I know we went 50,000. I don't know what does that change as far as your boom or the effect of the boom to get more altitude out of the cabin, or do you lose it because you can't pressurize?
So higher altitude gives you more attenuation.
But longer distance.
Right, longer distance to the ground, so you get more atmospheric attenuation in the signature. But higher altitude, you start getting into emissions challenges as well. And so some of the studies that we did, a number of years ago, said there's kind of a sweet spot that, nah. Right.
I mean, supersonic aircraft will fly much higher, you know, so.
Do you expect supersonic aircraft to come under fire, you know, as everybody's trying to reduce emissions? Do you expect, you know, public perception can certainly kill any program. Do you expect there to be criticisms?
Yes.
There
Yes.
already is.
Yeah, there already are.
It's nothing new. It's just a matter of informing everybody about the facts instead of just relying on a piece of information that's not factual. And there's a lot of that going on. As Rob mentioned, there's some people that believe that it's going to take tons of fuel to fly supersonically. Yes, it will take more, but it won't take tons of fuel given the advances that have occurred in technology. So there will be a lot of resistance, but it's a matter of educating everybody. And supersonics is coming. I honestly believe that. I can't give you an exact timeline, but I think it's definitely on its way, because I think the technical hurdles have been overcome now, and it's just a matter of overcoming the regulatory hurdles now.
And we're already working on that. We're already working on looking at emissions, looking at the noise, working with the FAA, going through modeling, starting to model what some of the aircraft will do. So it's very proactive, even though, yes, it'll be an issue, but it's all very proactive. So.
Yeah. So the answer is yes. There will be pushback. There will be a challenge with that. And again, it's about education. You know, I had a guy do a calculation one day on a block mission of a certain range. You know, take one of our subsonic airplanes and take a supersonic airplane and tell me how much more fuel. So he did that. He told me how much more fuel. It's like, okay, now do that with some blend of renewable fuel and tell me what the CO2 emissions are. Well, guess what? The supersonic flight was less CO2 than the subsonic flight.
Oh, wow.
Now someone would say, well, fantastic. Then let's do that on the subsonic airplanes. Why do we need to burn more fuel on the supersonic airplanes? You use supersonics to push forward the renewable fuel industry, and now take that renewable fuel industry and leverage it back onto the subsonic commercial operations. You've now enabled the development of a new industry that helps to combat what we're already challenged with on the subsonic market, right?
Yeah.
Now that said, you know, you got to do it right. You can't just immediately go legislate in that we're going to go do this. It's not ready. That is still an emergent market. Fuels aren't there. The technologies are just coming online. They've just started getting certification standards. But there's an opportunity there to really help to promote environmental consciousness across the entire aviation industry if we work together to do it.
That's great. That's fantastic. Oh, we have a question.
So kind of related to passenger comfort during maybe a supersonic flight, When you're talking about this flight profile, and it sounds like you may adjust, speed, altitude. How much do you expect that to be a constant change going on? I mean, are you going to feel any acceleration,
No,
or
not
is it
at
just
all.
a very subtle?
Right.
Okay.
So that's why you have all the prediction, right? When we do our flight plan, we're already looking at the weather and our forecasted data. We already have all that information that's out there. And believe it or not, weather, even from climate to climate, doesn't change that much. You really get the frontal boundary issues. Well, that will already be planned for. Even when you get to the aircraft, the changes, you're able to look at your flight plan and to modify it and everything. So once you're up at altitude, the idea is you really will not have to adjust your flight plan all that much because you've already planned it out. We did design in a weather monitoring system that actually monitors the weather changes, compares them to what's already loaded in your system, and will give the pilot an alert when they need to actually pay attention if it violates one of those thresholds. And then, but it still may be a minor change. Right, and you're not constantly, exactly. Matter of fact, one of the worst things you could do is do lots of banking to manage a supersonic because it creates focus booms. You even want it more subtle and more shallow. So in all actuality, your ride is probably going to be much, much smoother than even a normal.
Laura, it's interesting. I read a report, and I'm trying to remember, I think it was an environmental impact statement somewhere, and was talking about a fighter pilot who was at supersonic speed. He saw a town coming up, right? So what did he do? He took evasive action, right? He turned. Rather than slowing down or climbing or whatever, he turned. And when he turned, he did it in such a way that I guess it was very aggressive, right? So he did it in such a way that rather than putting a normal boom on the town, he put a focus boom on the town. Right?
Yeah, because what they don't realize is if you're seeing that town up here, you've already created that boom back there. So you really have to, that's the mental model change of how a pilot would fly. Our procedures might be the same, but how you think and how you fly an aircraft will be quite different. In those, you want a shallow turn. You don't want, acceleration points are really important in managing your boom.
It's interesting. I know we're running out of time. When you think about, most of us that are aero folks, we think about airflow, right? And so when you're going supersonic, you create a shock wave, and you've got this cone of a wave. It takes a while to calibrate yourself to flip from the aero reference frame to the acoustical reference frame, where the aircraft is here. You're creating a shock wave here. That shock wave is sending a ray that's going out over there, and propagation distance is how far?
Oh my gosh, it
10
could
miles?
be even more. Depends on where you're up and how you're going and how fast. So it actually changes. So the interesting thing, when you're at slow speed, your cone is narrower, so your propagation goes out much farther. As you speed up in the cone and you get to an accelerated flight at a higher speed, the cone actually widens. So your carpet widens, but it's also closer. So you actually are sending out, when you're at a lower speed, you're sending out a higher boom farther in front, but it's very narrow. It's not the wide carpet. So it's interesting that when you're a pilot, I know for me, I made that mental adjustment. Sometimes I can look at a flight plan and how it turns and all that aggressiveness, and I could draw you, where it's gonna go. It's very interesting how quickly you get to that, but it's even better when you have a display that's easy to read and shows you and confirms all that. But yeah, so it's thinking about those type of flight regimes.
Yeah.
Very interesting.
Well, thank you so much, and thank you for your questions and your attention. And I'm glad we have folks like yourselves, subject matter experts, concentrating on all the nuances of this to bring this to fruition. And thanks again for your time. Let's thank the panelists.